This is the derivative of the power. And consequently, what you want to do is to choose the sizes for each of the genes, for instance, the AMs, such that you satisfy this constraint subject to this constraint here. And this comes out from Lagrange multiplier optimization. But it's a very, very simple one. And what it is basically telling you is that the optimal decision actually depends on the derivative of this ROC function. Now remember, the derivative of the ROC function is telling you how much power you're going to gain by increasing alpha. If you increase alpha, if I give you more error possibility, then that will increase your power. But the important thing is the incremental increase there. But other than that, though, it must still be attenuated by how much you have already used. Okay, so you notice that term there, 1 minus AM. If I have already given you too much type 1 error, then it will penalize you. Okay, so there is the rate of change in the power, but then where are you now in the scale of the type 1 error probability? And this is the basic solution to the thing there. Here's a simple example just to illustrate that. This is the power function, for instance, in this case where you have normal, but this is the one that I wanted to show you. Okay, this is the case for the normal, for instance. This is the distribution of effect sizes. Okay, not all uniform. So lots of them are close to 0, but there are some large one. This is the effect size. This is the optimal size that you should use for the test. Okay, if the effect size is 4, then you should use a big size. If the effect size is 12, then you shouldn't use a big size in that situation. And then this is the power that you achieve, this comparison of tests. Okay, so the point there is that you shouldn't be using the same test for each of the tests that you will be implementing in the thing there. Now, here's the lesson to this one here. See, one of the problems when I started doing this is I said, what do I need to do if I need to optimize the test? Should I give the error probabilities to the ones that are performing the best? Okay? Or should I give it to the ones that are performing lowest? I was thinking that I should give it to the best performing tests, because there I say I'll discover with certainty. But it turns out, to my surprise, mathematically, that it wasn't the case. The lesson is that do not invest your size on those where you will not make discoveries, or those that you will certainly make discoveries. What you need to do is to invest your size in the middle portion. Okay, that's that plot that you see here. No size there, no size. Put the sizes in the middle portion. Okay, and why is that? It's like investing. Okay, if you have you're investing in stocks, you want to put it on those in which the rate of increase if you invest there will be good. Okay, but here's a more wicked consequence of this one here, and I was telling this to Sunil. I said, I give you $10,000, Sunil, to allocate for merit increases to your faculty, for instance. Whom should you give it? Okay, should you give it to the top performing guys? Or should you give it to the lowest performing guys? If you give it to the lowest performing guys, you will not get anything for it. If you give it to the top one, you knew that they were going to discover things anyway. But if you give it to the middle one, you will get the best differential effect in that situation. So it's kind of interestingly, it leads to a way in which you should distribute your merit increase. Of course, we hate it because we all work very hard. Yes, yeah. But here's a much more interesting one for the graduate students. If your advisor doesn't want to talk to you anymore, you make an appointment to your advisor and he says, oh, come back next week. Okay, you come back next week. He says, come back next week, I'm busy. There are only two possibilities. Either that you are working your butt very hard already. Okay, you're the top there now. That says, there's no point talking to this guy. Or you are not working hard at all. To the extent that he says, if I spend another hour with this student, there's no effect. So he wants to invest his time to those that are in the middle, because those are the ones that will get the best result. And so in some sense, when you think about this problem, it's a decision-making problem, but it's allocation of resources. It's actually an economic problem. I give him a maximum level of type 1 error probability of 0.05, okay? How is it going to allocate this to all these capital M decisions for the big department to get the best. Okay, that's the essence of the solution there. And it was very surprising because I didn't believe it in the beginning, and I kept looking for my error. I said something is wrong with this solution, and then later it dawned on me that I said it does make sense, isn't it? And of course, after you do the simulation, it does make sense. Okay, so here's, for instance, a comparison of the BH and then the new procedure that we had. This is the control. Okay. So that's for the BH is this one. We wanted the control to be 10%. All of them are below 10%. This is the MDR. These are parameters in the simulation. And then you notice that this one is always smaller than this one here. And so you actually improve the procedure by making this differential allocation of the sizes. Okay. This is another set of simulation. And then you also notice that thing there. Okay, so you actually improve, except that in the solution so far that we have here, I'm assuming that I know the effect sizes. Most probably we don't know that. And in fact, the medical people should be the one to tell us what effect sizes are you thinking. But then if you have 10,000 of these genes, it is going to be very difficult to do that. So one of the goals that we have here is actually to do this adaptively. Maybe the data could tell us, maybe a training data could tell us about the proper effect size. But then errors comes in. Now I have to consider the potential of errors in that situation. But it at least tells us how to proceed if I knew the effect sizes, how to allocate the sizes in that situation. And so I'll conclude here by simply putting this, and these are existing problems that we have here. And there are many methods that we could compare this, but there are a lot of other problems still that we need to consider. And in fact, one of my students who will be joining the Florida International approached this problem from a Bayesian point of view, and I'm getting more and more convinced that that is the right way to go, that it's a Bayesian approach, and maybe this procedure that we actually came up with from a very classical framework will just fall out as a Bayesian empirical-based procedure. But in a sense, it gives us a way to deal with the thing there. And I think I'll just acknowledge my student, Wensong. She's the one joining FIU this August. And then he was also my former student. He's at Oklahoma State now, graduated last year. The data actually came from my wife. She's a biologist, and so she asks me to analyze their data. And of course, I always tell her that I am completely unbribable. Yeah, so I said I'm a statistician and I couldn't be bribed. Okay, so when she tells me one time that she said, you know, one of the mice hasn't died yet. And she said, do you think if it died, I will get a significant result? And I have to be very careful. I have to examine that she doesn't kill that mouse. So it's hard to be working to a biologist or a medical person somehow. They never know what they're going to do. You know, and the first lesson that she had from me is about randomization. I had to instill in them that randomization, random allocation of units into the different groups is actually a crucial component in the design of experiments. And because at one time she had me analyze this data, and they were comparing to treatment group in a control group. And I noticed that the weights of the two groups were completely different, that you couldn't determine anything. And I said, how did you allocate these mice, by the way? I said, oh, we just look at it and then put this group there and then put this group there. I said, I will not analyze this data. You have to repeat the experiment. Of course, they don't like it, but you have to insist those and so on. So, but they have these experiments there, and then that's where the microarray came. And this paper actually, it was more a theoretical paper, as you might have noticed. It came out in the Annals just this February. It used to be, the first version of it was 55 pages, and they wouldn't touch it. They kept saying, reduce this. And finally the editor said, okay, if you reduce it to 30 pages, and then put all the technicalities in an online appendix, then we will accept it. And what could you do? Yeah, it's there if you want to see it. But the interesting thing about it is that you could actually optimize certain things there. Okay, you could optimize certain things by using the power. And in some sense, it kind of extends the problem that Niemann in person had solved, which is power is intrinsic if you are looking for optimality. And we had ignored that in this multiple decision setting. And I think this is kind of one way in which this actually comes in. Yeah. So, thank you.